Section 8.2 is called the quadratic formula. So just as a little review, to find the x-intercepts, which are also called roots and are also called zeros, we have a few techniques. The first technique is if it's basic, we just solve. Like if it's x plus 2 equals 0, we just bring the 2 on the other side and we say x is equal to -2. The second technique is factoring. And we talked about the 4 different types of factoring. We have GCF, we have grouping, we have trinomials, and we also have special cases. The third technique, if it doesn't factor, we talked about completing the square. But somebody a long time ago got tired of completing the square and saw that when we complete the square, we're really just doing the same 4 steps over and over and over again with different numbers. So what they did is they generalized to come up with the quadratic formula. And I'll show you where that comes from. Remember, when we solve, we go from the least aggressive to the most aggressive in order to solve polynomials. We want to make sure that we make the x-intercepts, roots, and zeros. In order to find those, we just set the polynomial equal to 0 and then solve it. So, completing the square is tedious, and it's not that fun. All right, so what we're going to do is let's generalize for any A, B, and C values. What I mean by this is if we have a quadratic equation in standard form, let's go ahead and complete the square and see what happens. The first step to complete the square was we isolate the variables. The next step was we factor out the leading coefficient. Next step is we take half of the middle and then square it. That's going to go here. So b squared over 4a squared. After that, we multiply it by a and then subtract. So we're going to be subtracting b squared over 4a. A times b squared over 4a squared would cancel out with one of the a's on the bottom. Let's try to combine the negative b squared over 4a with the c by getting a common denominator or multiplying the top and bottom by 4a. We'd get a times, remember, half of the middle like we discussed. And then this would be minus b squared plus 4ac all over 4a is equal to 0. Next step is we'll try to get the x by itself by subtracting this on both sides. And we get a times x plus b over 2a squared is equal to, this will cancel with this, and if we distribute the negative, we'll just get b squared minus 4ac all over 4a. We divide both sides by a or multiply by its reciprocal, we'd get x plus b over 2a squared is equal to b squared minus 4ac all over 4a squared. Taking the square root of both sides, we wind up with absolute value of x plus b over 2a is equal to the square root of b squared minus 4ac all over 2a. Let's get rid of the absolute value. By writing plus or minus over here. And then we'll just bring the b over 2a over. And we get x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And that's the quadratic formula. So just to write it a little bit simpler, the quadratic formula, which we can use if a polynomial factors to solve it, but if it doesn't factor and you don't want to complete the square, we use the quadratic formula, which says that if you have a quadratic equation in standard form, then the answer, you don't have to complete the square every time. We completed the square once and we generalized it to get negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Let's take a look at some examples using the quadratic formula. And I also just want to mention something before we move on called the discriminant. The discriminant would be what's inside the square root, or b squared minus 4ac. This tells us what's called the nature of roots. And when we're talking about nature, we just means what do the graph actually look like? So there's three different scenarios. If our discriminant is bigger than 0, we say that there's two real roots. Remember, a root is the same thing as a 0 or an x-intercept. What this means, and again, if the discriminant is greater than 0, this means that the graph crosses the x-axis in two locations. So this would be an example of two real roots. If, on the other hand, the discriminant is equal to 0, this would be an example of one real root. Which would look something like this. One real root would just touch the x-axis in one location. Remember, though, this is a quadratic equation, which means that there's two answers, right? So if you have an equation where you get a discriminant that's equal to 0, it would look something like this, where it's x minus 2 squared is equal to 0. You'd actually wind up getting the same answer twice. So we get x is equal to 2 and x equals 2. This is called a double root. So technically, you are still getting two answers like you're supposed to using the fundamental theorem of algebra, but it just so happens that your two answers are the same number. The last scenario that'll happen with the discriminant is if b squared minus 4ac is negative. We say that we would get two complex roots. Complex, remember, is a combination of imaginary and real. All this means is if you're taking the square root of a negative number, you wouldn't have any intersections of the x-axis. The graph would be a floater, something like this. So let's take a look at some examples using the quadratic formula. The directions are going to just be to solve and describe the nature of roots. And let's start with the first example. 4x squared minus 11x minus 3 is equal to 0. First thing, let's identify what A is, B is, and C. Next, we'll just put those numbers into our quadratic formula. And I like using parentheses to ensure that I put them in correctly. So remember, it's the opposite of B plus or minus the square root of b squared minus 4ac all over 2a. Simplifying this would be the opposite of negative 11, which is just positive 11, plus or minus the square root of, let's see, negative 11 squared minus 4 times negative 3 is just 169 over 8. The square root of 169 is a perfect square. So because this is a perfect square, we want to make sure that we simplify our answer. So what that means is we're going to write x is equal to 11 plus or minus 13 over 8. Let's actually add 13. Divide by 8. So 24 divided by 8 is 3. And if we subtract 13, we get negative 2 over 8, which is just negative 1/4. Two answers, two real answers, because the discriminant is 169. The discriminant's the number inside the square root. That's bigger than 0, so this graph would look something like this. It would cross at 3 and negative 1/4. And that's what the graph would look like. What if we had an example where 9x squared minus 42x plus 49 is equal to 0? We know that A is 9, B is negative 42, and C is 49. So using our quadratic formula, we'll take the opposite of B plus or minus the square root of b squared minus 4ac all divided by 2a, or 42 plus or minus, let's see, negative 42 squared minus 4 times 9 times 49 is 0. Now, if the discriminant is 0, what that means is that there's going to just be one real answer. And let's see what that is. Square root of 0 is 0. 42 over 18 reduces to just 7 over 3. So that is the one real answer. And this graph will look something like this. 7/3 is 2 1/3, which is maybe over here. And the graph is going to look roughly like this. It'll have one real root. What if we had x plus 5 times x plus 1 is equal to 10x? Now, in order to solve this, we want to make sure that it's equal to 0. So I'm going to go ahead and distribute here, x squared plus x plus 5x plus 5, and then I'll bring the 10x over. So simplifying, we'd get x squared plus 6x minus 10x plus 5 is 0, or just x squared minus 4x plus 5 is 0. I don't think we could factor this, so we do have to use quadratic formula, where a is 1, b is -4, and c is 5. So we'll say that x is equal to the opposite of b, plus or minus the square root of b squared minus 4ac all over 2a, or 4 plus or minus the square root of 16 minus 20 would just be -4. We did talk about how to handle negative square roots, which would be the square root of 4 times the square root of -1, or 2i. And to simplify this, because that radical can be simplified to 2i, we could do 4 divided by 2 and 2i divided by 2. These would be our roots. And as you can see, there's 2 complex roots because our discriminant, which is -4, is less than 0. So that's why there's 2 complex roots. And this graph would look something like this. It's never going to touch the x-axis. We'll do one more problem. And what if we had 2x squared plus 19 is equal to 14x? First step is let's go ahead and make it equal to 0. So 2x squared minus 14x plus 19 is equal to 0. A would be 2, B would be -14, and C would be 19. X would be the opposite of B, plus or minus the square root of B squared minus 4AC, all divided by 2A. Or 14 plus or minus, let's see what this square root is, -14 squared minus 4 times 2 times 19 is 44 over 4. We'll simplify that square root to just be the square root of 4 times the square root of 11, or 2 root 11. And taking a look at this fraction, it looks like we have a common factor between the top and the bottom. We could take a 2 out of both the numerator and the denominator. So our final answer would just be x is equal to 7 plus or minus the square root of 11 over 2. If you wanted to convert these to a decimal, you could do that afterwards. I would only accept the perfect answer, but if we're going to do 7 plus the square root of 11 and divide by 2, one of the answers, if we add, would be 5.2. And one of the answers, if we subtract, would be 1.8. So what this means on our graph is that it crosses at a little more than 5 and a little before 2. The graph would look something like this. You would only convert to decimals to graph it. We do know that there's supposed to be 2 real roots because our discriminant is square root of 40, is just the 44. This means that there's 2 real roots. You wouldn't use the 11 because that radical has been modified. Use the original, just whatever b squared minus 4ac is. That's your discriminant.